Hello, my name is Kyle Luck, and I'm an undergrad at the University of Michigan, working for the Department of Materials Science and Engineering. I would like to acknowledge the mentorship of my faculty advisor, Max Stein, and two graduate students, Sarjo Biswas and Stephen Morris. My research is focused on organic solar cells. We are motivated to look into solar electricity because the U.S. primarily relies on the combustion of fossil fuels, a non-renewable resource, to meet its ever-increasing energy demands. Sunlight is an abundant, renewable energy resource. The amount of energy the Earth receives from the sun every hour is greater than the amount of energy the U.S. consumes each year. Shown in the upper left, the red square shows the area in the U.S. that, covered with 10% efficient solar cells, would generate enough energy to satisfy the national requirement. The small black dot in the center shows the relative worldwide area of solar cells installed and manufactured. They are currently too expensive to compete with fossil fuels for cost-effective energy generation. This is more explicitly shown below. This plot shows inorganic solar cell module price versus cumulative production. As production increases, module price decreases. However, these economies of scale is not enough for solar cells to compete with fossil fuels for cost-effective energy generation. For that to happen, solar cells would have to be at the red arrow, which falls significantly below the projected trend line. Organic solar cells have the potential to meet this goal. Shown in the upper right are typical organic materials used in organic cells. CUPC is manufactured in extremely large quantities each year for use in the textile industry and as dyes for paints, demonstrating our ability to manufacture these materials on an industrial scale. However, organic solar cell efficiency is currently less than organic solar cells, and for them to compete with fossil fuels, more research needs to be done to raise their efficiencies. A typical organic cell consists of photoactive organic materials sandwiched between metal electrodes. A typical device is around a few hundred nanometers thick. All efficient organic cells use at least two organic components, electron donor and acceptor films. Incident light generates a bound electron hole pair, an exciton, which must diffuse to the interface between these two materials. It is then separated into a free electron and hole, and the separated particles are collected at the electrodes, generating a current. We typically want thicker films for better light absorption. However, excitons have finite diffusion lengths, and those that don't make it to the interface decay as heat, and no current is collected. Therefore, there is a maximum film thickness for decent efficiencies. Power conversion efficiency for solar cells is shown on the bottom right. It is governed by three parameters. JSC, how much current do we pull out of the cell? VOC, at which voltage do we stop generating usable current? And FF, a measure of the series resistance of the cell. There are typically trade-offs between these three parameters. And P incident is the incident power density. How much light are we shining on the cell? We are specifically looking at improving the VOC. It has been shown to be linearly related between the energy gap of the lowest occupied molecular orbital of the acceptor material and the highest occupied molecular orbital of the donor material, minus the exciton binding energy, E sub B. We are atmospherically exposing the donor material to oxygen, lowering its Fermi level E sub F. This will decrease E sub B, increasing the VOC term, as qualitatively shown in the plot on the right. However, there is a trade-off. If the exciton binding energy is smaller, the drive for an exciton to be dissociated to the interface is decreased, so less current is collected. And the power conversion efficiencies of an undoped and oxygen-doped cell are about the same. So we are trying to more fully understand why and see if we can optimize the trade-off between the voltage and the current collected. I want to thank the SURE program for the research experience. It's a great way to test drive your interest and potential for grad school.